All right, the skinny on fats. So the correct word to describe the broad category that we're about of macromolecules that we're about to wade into is lipids. These are fats and oils. Fats are lipids that, in general, are solid at room temperature, and oils are liquid at room temperature. It's purely fats and oils. It's purely a physical description, and we use lipids as an energy source for muscle, liver, and kidneys. But they do a whole lot more for us, and we're only going to look at, this isn't a physiology class, so I'm not going to get super deep into everything that lipids do for us. But as far as we're concerned, they are an energy source, an energy reserve. All right. This section is not going to get into that aspect of it too deeply. I'm going to just try to show you what they are so that when I get to metabolism, which is the next unit I'm going to talk about, you'll have the basic vocabulary to understand how our body uses energy. All right. So yeah, this is the third out of the four categories of biomolecules that I started talking about so many weeks ago. And the most basic category of lipid, and there's probably, I don't know, something like 8 different very general categories of lipids. The most fundamental, the most ubiquitous, the most conceptually accessible of them is the fatty acids. A lot of other more complicated lipid structures are built out of fatty acids. All right, so for example, steroid hormones. The steroid hormones, the carbon in them is going to be derived from fatty acids. All right, cholesterol, etc., coming from the fatty acids. So what is a fatty acid? You've seen these already this semester in lab. They've gone by a number of different names. What were some names I used for fatty acids in the lab? Throw your mind back. Just a scant 2 weeks ago in lab. What did we do? That was the really messy lab with the red dye and the oil and the water and the blenders and the microscopes. Yeah, what?
Was that the emulsions?
Yeah, emulsions. Yep. And a lot of what we're going to be doing today is setting the groundwork to talk about emulsions later in the week. So we talked about emulsifiers, like the fatty acids that are found in egg yolk. That was one. We also called them detergents. We also called them surfactants. Detergents because they're able to take greasy dirt and solubilize them. Surfactants because they're able to form a surface, a lipid bilayer surface that can be a boundary between hydrophobic and hydrophilic media. But now we're calling them fatty acids. And a fatty acid is an example of a much more general category of compound called amphipaths. It is amphipathic. An amphipathic molecule is one that has a hydrophobic portion of it and a hydrophilic portion. So in fatty acids, we have this long hydrocarbon chain. It's just carbon and hydrogen. There's nothing else. No more oxygens. Notice I'm not putting some like CH2O subscript N up here to give you a generalized empirical formula for fatty acids. It doesn't actually work that way with fatty acids. You'll appreciate the structural integrity of them soon here. So we have this long hydrocarbon chain, and then on the other end of it is simply a carboxylic acid. So I'm going to hand one of these around. This is a sort of abbreviated fatty acid. It's a pretty short chain fatty acid. In fact, you can tell me whether you think this would be a lipid or oil. You have, you guys can, you don't have to do that now, but you can contemplate it. And you'll notice something else sort of weird about that as we hand it around. That'll come to light in a bit. So this greasy hydrocarbon chain is anywhere from 4 to 24 carbons long. 4 is exceptionally short, and 24 is unusually long. Most of them are in the teens somewhere. And if you were going to come up with an equivalent formula for what a fatty acid, the chemical formula for a fatty acid like we had, the CH2O subscript N for carbohydrates, it would be this abbreviated structure here. So you have a methyl group on the end, and then these CH2 groups in the middle. There's a subscript 10 because that happens to be the fatty acid that I have on the board. And then there's the acid group, the carboxylic acid on the end of it. But that subscript 10 could easily be changed to an N to represent the general formula for a fatty acid. Okay, so a methyl group on the end and just a long chain of CH2 groups and then an acid on the end. Are there any questions? All right. So these fatty acids, the hydrophobic portion, the hydrocarbon chain on the end, it doesn't want to be in solution. It's not polarizable. So when water is around, when it's forced into water, it causes a local ordering of the water structure. Now, you know, this is a 100 level class for non-majors, so like a deeper discussion of what entropy is and how entropy is an organizing force in the universe. Entropy just meaning disorder is probably way beyond the scope of where I need to go. But I'll just say there are entropic reasons why water does not want to be around greasy, non-polarizable things. It likes to, water's kind of pushy and wants to like dictate the scene. And when it's forced to be next to a greasy chain, it's not really able to do that. All right, so and to minimize the entropic cost on the solvent, these greasy tails just align themselves. So we see here in this zoomed in bubble, we see these little fingers sticking down with the little gold beads along the top. The gold bead is meant to represent the carboxylic acid, the polar head group that is happy to be exposed to the water. And the little fingers sticking down are the long greasy tails that are equally happy to be next to one another in a hydrophobic environment, a non-polarized or polarizable environment. But on the bottom of that, you can't just have the bottom of those greasy tails open to water on the other side of the wall, so we get this bilayer effect. We have two layers, a layer of upward or outward facing fatty acids or lipids, and a layer of downward or inward facing fatty acids or lipids. We get this lipid bilayer. And does anyone remember when they were kids blowing bubbles? I mean, many of you must have done that. Sometimes if you go around like a bubble blowing pro, you can get, you know, when you look at a bubble, it has that beautiful sort of opalescent sheen on it, okay? Just like you would see in a rainstorm in a parking lot where oil that's dripped from a car creates that sort of rainbow pattern on the surface of water, right? So you're familiar with this color phenomenon I'm talking about. Well, in those bubbles, that is a bilayer. It is a detergent bilayer from the soap. that's creating those bubbles. Like real bubble pros are sometime, I don't know, I actually haven't looked it up in a real long time, but I've seen firsthand and videos of people who are able to pop the bubble, but only one layer of the bilayer can collapse, and the other layer can actually stay intact, exposed to the air. So that's kind of something fun to look at. Anyways, our cells are not tremendously different than a soap bubble that you may blow. Just these lipid bilayers. But instead of being filled with air, they're filled with water, and they're surrounded by water. All right. So I started by talking about how lipids were used as energy sources for our cells, but they are also incredibly important structural components. All of our cells are made of lipids. They're essential to any form of life on the planet. Well, fatty acids, so this fatty acid I handed around, what did you guys notice about this thing? Yeah, what's that, son? Did somebody say something? Come on, speak up. I know it's Monday. Yeah, Damon.
It doesn't have like a ton of molecular diversity.
Nope, doesn't have a ton of molecular diversity for sure. Yeah, it's a long carbon chain right up there. And then there's this acid group down here. What else, Hannah?
There's the double bond in the middle.
Oh, good. Yeah, that's what I wanted you to tell me. Yeah, there's this double bond in the middle. And what did you notice about this double bond? Here, I'll hand it around again. Inspect, draw your attention directly to that double bond. And I want you to compare the way the double bond functions structurally in that molecule to the way any of the other bonds in the chain. So mess with the other bonds and see what they do, and then compare that to the function of that double bond. So there are two types of fatty acids. They're saturated and unsaturated. A saturated fatty acid is one in which there are no double bonds. The only double bond would be in the carbonyl group of the acid. All right, but that's a terminal double bond, and it's part of the polar head group. Not important to our discussion here. Unsaturated fatty acids. So when I say saturated, saturated means that all of the carbons are saturated with hydrogen. What does it mean to be saturated? If you have a sponge, how do you saturate a sponge?
Get it wet.
Yeah, you get it wet and you fill it up till the brimming point with water, all right? That's what saturated means. And in this case, the carbons are carrying, each of them, as much hydrogen as they possibly can in a saturated fat. There are no alkene groups. Alkene is the chemical term for a double bond between carbons, all right? An alkane are carbons that are single bonded to one another. Alkene is double bonds. So unsaturated fats are going to have anywhere from one to many double bonds between carbons. All right? Now, these double bonds can either be cis or trans, and we'll understand what that means in a moment. Only cis double bonds occur naturally. Only cis occurs naturally. So here is a structure of oleic acid, which is it's a type of fatty acid. It's got a long carbon chain of what? 14, 15, 16, 17, 18 carbons, and an acid on the end. And then at the ninth carbon, there is a double bond between the 9th and 10th carbon. Counting C1 would be at the methyl group on the left. All right? So we see the abbreviated structure and the line structure of oleic acid. What do you notice about that double bond? As you guys have handed it around, what is your observation of it now?
It's right in the middle.
It's right in the middle. I did that. Yeah, I put it there in the middle. What else about it? You keep thinking about it. Keep passing it around, and we'll answer it. So a monounsaturated fatty acid is a fatty acid that only has one double bond in it. All right, only one. And a polyunsaturated fat, a polyunsaturated fatty acid, has more than one. You've probably heard these terms before. Who's never heard polyunsaturated fat before? Any of you? So you've all heard these terms, right? Because they are used in common parlance quite a bit. So we can describe the position of the double bond using what's called the omega system. Omega. And there are no fraternities on campus. But I think we do they teach Greek as a language on campus? Does anybody know what letter of the Greek alphabet omega is? It is the last one, the alpha and the omega. All right. So the omega carbon is the last carbon, and it turns out that it's a good reference point because the chemical properties, the metabolic properties of these fatty acids, the position is dictated by their double bonds, but most specifically the relationship of those double bonds to that last carbon. Why is that? Well, because these fatty acids grow along the omega end, or are cleaved along the omega end. We're going to build a fatty acid by growing that chain, and we're going to break it down by shortening that chain from that omega end. So the relationship of the double bond is in relationship to the omega carbon. So here is a lipid. How many are there? There's 2, 4, 6, 8, 10, 12, 14, 16, 18. So that's with 2 double bonds and omega-6. That's probably something like a icosanoid of some sort, an icosanoic acid or something. I don't actually remember, but it doesn't matter. This fat is called an omega-6 polyunsaturated fat because the 6th bond, the 6th carbon-carbon bond from that omega carbon is the first point of unsaturation. All right, it's an omega-6 fatty acid. And there's going to be a family of omega-6 fatty acids. You can have an omega-6 monounsaturated fatty acid. You can have di or polyunsaturated fatty acid, but it falls within a category of omega-6 because of the distance of that double bond from the end of that carbon chain. I know this doesn't seem particularly important yet, but it does have pretty important health consequences in terms of the foods you eat and the types of lipids that are in them. All right, so now, Damon, the fat is in your hands. Please tell me, what do you notice about that double bond?
It's like flexible.
Okay, you're bending it, yeah. And that is certainly a consequence of the fact that that thing is not actually a fat, but made of plastic.
Oh.
Okay, but I like the way you're thinking. You're on the right track.
I remember what you were saying about like the ability of some chains to like.
Yeah, that they can bend, they can flex. Most importantly, I'm talking about rotation. So look at some of the single bonds. Yeah, try to change the shape of that without unconnecting and reconnecting bonds. Just change the shape of that. You have it mostly as a bowl, right? Yeah, look at that. Wow, you can swing that tail around. You can bring the head, can swing around, whatever. It can contort in all kinds of shapes. All of those single bonds can rotate. All right? Try the double bond. Can we rotate around that double bond? Cannot do that. Cannot do that. So that double bond is called cis because the two chains, that come out of the carbons that are double bonded to one another are on the same side of the double bond. You see how they're emerging from the same side of the double bond? Imagine that the double bond is a plane and they're both coming up out of the top side now. That's called a cis fatty acid. However, I could break that bond and reconfigure it so that it would be trans, and the chains would be emerging from either side, opposite sides of that fatty acid. So I'm sure all of you have heard about trans fats before. This is what a trans fat is. A trans fat is a normal, healthy, cis fatty acid that has somehow, by some human interference, become a trans fatty acid. And this can happen through a number of means. It can happen probably most easily by heating it, heating some particularly unstable cis fatty acids. I isomerize them to a trans fatty acid. So here's our friend oleic acid again that I showed you in the beginning. And it has a double bond at, what is that there? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's an omega-9 fatty acid. And in the bottom is the cis oleic variant. And the carbon chains are emerging from the same side of the double bond. And say we want to cook with this stuff, we heat it up, and that fat isomerizes. It flips. So it has the same molecular connectivity, but they're not superimposable. Okay, so we've changed the stereochemistry of this molecule. Well, why would a trans fatty acid be any worse for us than a cis fatty acid? You'll just have to take my word for that for the moment. We will answer that question. All right, that's one of the important questions that we're after. Yes.
Can you flip it back by heating a trans?
Turns out that a cis fatty acid is actually higher in energy than a trans fatty acid. I'm going to break my promise to not use the board here, but let's see, maybe I can get this camera right. So if this is energy and this is time, right here would be your cis, and then you're going to heat it, you're going to put some energy in, you're going to get over this bump, and you're going to get down here to the trans. So the energy it takes to go from trans back to a cis is significant. It's significant. And it's the kind of thing that you would have to have some kind of isomerase or something, some kind of enzyme to make this barrier go down. So you can do that and to facilitate that reaction. Just by heating a trans fatty acid, you are not going backwards. Yeah. It's like the reaction is basically like this with a little bit like that. All right?
How much heat do you need to go from cis to trans?
Good question. Depends on the fat. That's why there are good cooking oils and bad cooking oils. All right? There's
So
like
bad ones just take more heat to
less heat.
less heat.
Like a poor cooking oil would be like flaxseed oil, linoleic acid. It takes very little heat to get over that boundary.
Why is that?
It has to do with the chain length, the position of the degree of unsaturation, the position of the unsaturation. All very good questions. Well, we're going to explore that a little bit more, so just be patient. All right, so here are some common fatty acids. I'm not going to put you guys all to sleep by going through the vast array of fatty acids that are possible, but take my word for it that similar but certainly not to the same degree as carbohydrates, but similar to carbohydrates, there is a wide degree of structural diversity that's possible in this category of molecules. There's a lot of different possible lengths and saturation patterns in lipids, as you can begin to appreciate. All right. Here's ones that you find in nature commonly. So I'm going to start with caprylic acid. This is one of these MCL lipids that, has anyone heard of the ketogenic diet before, or like super elite trainers are into this stuff, like really high performance athletes? Like caprylic acid, it's a medium length fatty acid that is found in coconut oil and is particularly easy for the body to metabolize. It's actually quite a healthy oil for you, and it's easy to metabolize, easy to get energy out of, and this thing called, like, for example, the bulletproof diet is based upon consuming large quantities of caprylic acid. It's something that, like elite athletes are into. But it is a saturated fat. There are no double bonds in it. Lauric acid, 12, myristic acid, 14, palmitic acid, 16, stearic acid, 18, oleic, we've already seen. Oleic acid is the first one on this list that actually has a double bond. So we're getting into the unsaturated fatty acids. You'll notice here that the ones that I'm showing you, as the chain length goes up, so does the degree of unsaturation. All right, and there's a biophysical reason that nature has taken advantage of that. All right, so the shorter the oil, or the shorter the fatty acid, the more likely it is to be an oil versus a fat, meaning the more likely it is to have a lower melting point. And the higher the degree of unsaturation, the lower the melting point. All right, so as you get these longer molecules, to keep them pliable, we add unsaturation. Yes, Damon?
I was just going to ask you to repeat those last 2 points.
Yeah. So as you increase the molecular weight or the chain length of an acid, as you increase that chain length, you are increasing the melting point. And as you increase the saturation, you are decreasing the melting point. So nature has taken advantage of those two properties to sort of mitigate the effects of long-chain fatty acids by incorporating unsaturation into it to tune in the biophysical properties that fat needs. Yeah. So there's like a host of these other acids on the list here, and we're going to go through some of them. But these are all for people who get way into it. These are going to be usual suspects, and there's a lot to learn about each of them. Some of probably the most important ones on here are alpha-linolenic acid. You find linolenic in linseed oil, which is why it's called linolenic acid. It was originally derived from linseeds, which are the seeds of the flax plant, which is the plant that linen is made out of. But alpha-linolenic acid is also found in fish oil and seaweed, which is probably why it's in fish oil. There's a gamma-linolenic acid. That's an omega-6 fatty acid. Arachidonic acid is extremely important as a precursor to various steroid hormones. Eicosapentaenoic acid, EPA, and docosahexaenoic acid, DHA. EPA and DHA. Eicosa is a prefix that refers to fish. So this fatty acid is particularly found in fish oil. But EPA and DHA have been identified as extremely important anti-inflammatory fatty acids. They lead to the synthesis of different steroid hormones in the body that are profoundly beneficial. And you find these kinds of fats with a degree of unsaturation like that. You find these kinds of fats in a lot of plant sources and fish. All right, so let's take all of this and break it down into a sort of scheme. So we have fatty acids. They can be saturated or unsaturated. Amongst the saturated fatty acids, here's just a few examples so that you get a sense of them. This family of them: lauric acid, myristic acid, palmitic acid, stearic acid. We find these saturated fats, and in general, saturated fats are found mostly in animal products. So animal fat like butter, cream, etc., human breast milk, etc., etc. But you also find them in a lot of plant fats that come from the warmer regions of the planet, because they have they're fully saturated. What did I say about saturation and melting temperature? The more unsaturation there is, the lower the melting point. So these are fully saturated, so you expect them to have a higher melting point. All right, so these fatty acids are going to be fluid in a warmer climate, which is why you also find them in palm oil and coconut oil. All right, these tend to be much more heat stable fatty acids. All right, palms and coconuts, tropical. Okay. So then there are unsaturated fatty acids, and within them there can be either mono or poly. Within the monounsaturated fatty acids, probably the most important one, the most common one certainly, is oleic acid, this one that I've showed you multiple times yet today. And this is an omega-9 fatty acid. It has the 9th carbon-carbon bond from the end is where the unsaturation is. It's right in the middle. It's an 18 carbon chain. And we find this in a mixture of fatty acid, in a mixture of vegetable and animal sources. Okay, so we see it in olive oil. Olive oil, in fact, is mostly oleic acid, which is why we even call it oleic acid. Oleo is made from olive oil and eggs. So oleic acid is the richest source that you can find out there. Is really good virgin pressed olive oil. 83 up to 83% of olive oil is just this stuff. It's in pecan oil, canola, peanut oil is pretty high, macadamia oil if you want to get fancy. Sunflower oil is even potentially a higher source. There's a lot of variants of sunflower oil. Even grapeseed, sesame oil, and lower quantities in poppy seed oil. It is not excluded from animal fat as well, though. So poultry is about half. The fat from poultry is about half oleic acid, which is what is that stuff called? Does anybody here have Jewish heritage in their family where they cook? What is that stuff called? Scrapple? No one? You know what I'm talking about?
I know what it is.
Yeah. It's rendered schmaltz is what it is, and then they make the scrapple with the chicken skin. But schmaltz is rendered chicken fat, which is not remarkably different than olive oil, actually. And then about half of the fat in lard, rendered lard, is also oleic acid. All right, so polyunsaturated. And amongst the polyunsaturated fats, I'm only going to make the distinction here between the omega-3 and omega-6s because these are by far the most important and common ones. First, the omega-6 fatty acids. The most common of them, as I showed you in the previous slide, are linolenic acid and CLA, GLA, and arachidonic acid. These range in size from 18 to 22 carbons in length, and we can see that they are omega-6 because the omega carbon is labeled on each of them, and if you count bonds over, you can see that that sixth position is where we have the unsaturation. These are linoleic acid and arachidonic acid. They are important precursors to various steroid hormones, as I talked about earlier. We'll see a bit of that later. Then the omega-3 fatty acids. So linolenic is different than linoleic. Both of them are derived from or found in lots of plant sources, but are highly concentrated in linseed oil or flax oil. So does anyone's parents use flaxseed oil like on their salads or anything like that? Has anyone ever had it before? Yeah. It tastes. What does it taste like to you?
I don't know if I had the oil. I had like actual flaxseed.
Yeah, flaxseed, sure. Yep, high in fiber. Yeah. Well, anyways, linolenic acid is derived from the crushed linseeds, and these are all omega-3 fatty acids. So if you look at that terminal carbon there, the third bond over is a double bond in each of these: linolenic, icosapentaenoic, and docosahexaenoic acids. These acids would be really horrible cooking oils. They are not for cooking. In fact, they are so heat unstable that they should be refrigerated. Linolenic acid is the principal component of linseed oil, which is an excellent salad dressing oil kept in the fridge. But when it is boiled, all of those double bonds that you see there in the linolenic acid turn to trans, and we call that boiled linseed oil, which they use as an old school varnish. They use it as a wood varnish. So maybe you've heard of it. It's also used. Has anyone done oil painting before? Yeah. So that smell that is distinctive of oil paints is that fat, but all trans because it's been boiled. So I think that's all the time I have today. But we'll pick up here next time, and we'll talk about these double bonds and why they're important. Okay?
Are fish mostly known for like omega-3 fatty acids? Right?
There's omega-3s. There are omega-6s in there, but yeah, they're known for the omega-3s. Yep. Yeah, that's
So
the fat that you want in your diet.
That's different from, like, they're not saturated, is it? You said that.
No, they're
fats
polyunsaturated fats.
Okay.